An index set v1 through vp of two or more vectors with v1 not equal to 0 vector is linearly dependent if and only if some v sub j where with j greater than 1 is a linear combination of the preceding vectors. Let's look at an example to reinforce this statement. Let p sub 1 of t equal 1, p sub 2 of t equal t, and p sub 3 of t equal 4 minus t. This is not a linearly independent set. In fact, the set p1 through p3 is linearly dependent in the set of polynomials because the third polynomial can be written as a combination of the first two. If you take 4 times p1, that gives you 4, minus p2, that'll be negative t, that actually comes exactly out to p3. So linearly dependent if any of them can be written as a linear combination of the other ones, specifically the preceding ones. The set sine of t, cosine of t is linearly independent on the closed interval 0 to 1. That's the space of all continuous functions where t is 0 to 1 inclusive. Since sine of t and cosine of t are not multiples of one another as vectors in that closed interval, they are linearly independent. And what that means is there's no constant value or c or scalar where one of your trig functions is a constant multiplier or scalar of the other, and that just counts for all t in that closed interval. Now, a counterexample to that would be, say you had sine of 2t and sine t cosine t. If you think back to trig, sine of 2t is an identity for a double angle where you have 2 times sine t cosine t. So this would be a case of linearly dependent because one of them can be written as a scalar multiple of the other. Let H be a subspace of a vector space V. An index set of vectors b1 through bp that are in that vector space is a basis for H if B is a linearly independent set and the subspace spanned by B coincides with H. That is, H is equal to the span of those P vectors. Let's look at some examples. Let A be an invertible matrix where we have columns 1 through n. The columns of A form a basis for Rn because they are linearly independent and they span Rn. And this is by the invertible matrix theorem. Back in the determinants and matrices notes on Google Drive, there's one of those where I put a PowerPoint presentation in there, and it lists all of those properties of the invertible matrix theorem. But again, because it's invertible, there will be a pivot in every column, so linearly independent. No column can be written as a scalar combination or a linear combination of any of the other ones preceding it. A second example, let E1 through En be the columns of an n by n identity matrix. E sub 1, the first position is 1, the rest are 0. E sub 2, the second position is 1, the rest are 0, and so forth till you get to the end where the nth position is 1 and the rest are zeros. This set of vectors is called the standard basis for Rn. For R3 specifically, we take x1, x2, and x3, and then we just have the unit length 1, 0, 0, 0, 1, 0, and then 0, 0, 1, those basis vectors. The next example, we have three vectors. Each one of them has three entries. Determine if these three vectors is the basis for R3. Okay, so what we'll do is we'll create a matrix A using these three columns, V1, V2, V3. There's several different ways to do this. I just want to show you a couple. First thing is the determinant of A is non-zero, therefore it's invertible. If you were to take matrix A and put it into your calculator or on an online website where you have a matrix calculator, either way you want to do it, if you row reduce matrix A, you have a pivot in every column. So these are linearly independent. Therefore, the columns of A form a basis for R3. Let S be the set 1t, t squared, and keep working your way up to t to the nth power. That's a standard basis for polynomials of n degree. First, S spans Pm. None of these entries can be written as a linear combination of the other. They're all independent. In fact, S is linearly independent because one thing we can check is if we have all these coefficients of these, and if you can call them vectors, we have 1t, t squared, all the way up to tn, but we're putting in these scalar multipliers. If the only way this is going to be equal to a zero polynomial is if every one of those coefficients is zero. So for the left side to equal the zero polynomial, by fundamental theorem of algebra, all these coefficients have to be zero. The spanning set theorem says if we take S to be a set of P vectors, V1 through Vp, and those are in vector space V, and we let H be the span of those P vectors, if one of the vectors in S, say V sub k, is a linear combination of the remaining vectors in S, then the set formed from S, which is those P vectors, by removing Vk, still spans H. Okay, so if one in particular can be written as a linear combination of the others, you can remove that particular vector and your set will still span H. It's sort of pulling out a redundant column if you were to write those vectors in a matrix format. Part B, if H is not the empty set, then some subset of S is a basis for H. So let's look at an example. We have three vectors, V1, 2, and 3, and we're going to say H is the span of those three vectors. Since the third vector is a linear combination of the first two, specifically 5 times V1 plus 3 times V2, 5 times 0 plus 3 times 2 is 6, 5 times 2 plus 3 times 2, that's 16, 5 times negative 1 plus 3 times 0. Okay, so essentially you can remove V3, and that's in fact what we're going to do. Since V3 is a linear combination of the first two, we can show that the span of those three vectors up here is equal to the span of just the first two. Now how do we do that? Every vector in the span of V1, V2 belongs to H because H is the span of P. We can write C1V1 plus C2V2 as C1V1 plus C2V2 plus 0 times V3. All right, so what we'll do now is we're going to pick an X to be a vector in H. That vector will have weights attached to the vectors, C1, V1, C2, V2, C3, V3. But if you replace V3 with 5V1 plus 3V2, because up here in the note we saw that V3 can be replaced with those two. Okay, now separate and sort, or maybe you want to sort and separate. V1 has a C1 and a 5C3 attached. V2 has C2 and 3C3 attached. So you can rewrite that three terms as a linear combination of just the first two, V1, V2. I rearranged, since these are inside the parentheses are going to be constants, I just call them M and N. But anyway, you pick a vector with all three components using the fact that V3 is a linear combination of the first two. Your vector's in the span of just the first two vectors. It's a linear combination, and H. And the span of V1, V2 are the same set of vectors. Basically, you just remove the one that's repetitive. Or maybe I shouldn't say repetitive, maybe just say remove any vectors that can be written as linear combinations of the others. There we go. So those first two vectors is a basis of H. The pivot columns of a matrix A form a basis for column A. Now, I just want to casually mention pivot rows. Those rows make up what's called a row space. And you might see that show up in your homework, row space. I'll remind you down once we get going on a problem. Example, let matrix A, we've got a 4x5 matrix. We're supposed to find a basis of the column. Okay, so for column space, if you want to find a basis for your column space, take your matrix, row reduce it, find your pivot positions, and due to pivots A2 and A4, that column doesn't have a pivot. The fourth one doesn't either. Then what that means is A2 and A4 are free variables. So by the spanning set theorem, the second and fourth column can be discarded. And we can use A1, A3, and A5, which first, third, fifth columns have a pivot. Then we can take S to be this first, the set of vectors of the first, third, and fifth columns. It's totally fine to use the row reduced columns, the first, third, and the fifth, because those will be a basis for your column space. I do want to point out, if you happen to be asked about a row space, find your pivots after you reduce. Row 1, row 2, and row 3 would be your row space of matrix A. These three vectors down here, you can go back to the original matrix and pull out your first, third, and fifth columns and write those. That's totally fine. The three vectors that have pivots in each column, first, third, and fifth, those are linearly independent. And then just for some extra examples that might help you with your homework, let's take two vectors, V1 and V2. Let's determine if those two vectors is a basis for R3. Is V1, V2, the set of those two vectors, a basis for R2? Well, let's check it out. Let's take matrix A and form it by using V1 and V2 as its columns. And then we'll row reduce it. We have a pivot in the first column, a pivot in the second column. The problem is we don't have any thing down here in the third row. Now, since not every row of A contains a pivot position, the columns of A do not span R3. Let me read that again. Not every row of A contains a pivot position, so the columns of A don't span R3. Therefore, V1 and V2 is not a basis for R3. Now, since V1 and V2 are not in R2 because they have 3 entries, they can't be a basis for R2 either. And then the third comment, since V1 and V2 are linearly independent, and that is due to column pivots, both columns have a pivot, they are a basis for a subspace of R3, specifically the span of the two vectors in the beginning. Example 2, we have 4 vectors. Find a basis for the subspace W spanned by V1 through V4. Create matrix A using the 4 vectors as columns. Row reduce and note your pivots. We have a pivot in the first column, a pivot in the second column, and that's it. We do have a consistent, if you were to set up an augmented matrix and try to find a solution, we do have a row of zeros, which is fine. The first 2 columns of A are the pivot columns and form a basis of the column space. So V1 and V2 is a basis for W. Let V1, V2, and H, and this is the third example, sorry y'all, I might have jumped ahead too fast. So we're going to take V1 and V2, and we're going to let H be defined as a column vector of a real number, the same real number, and 0. Every vector in H is a linear combination of V1 and V2. Why is that? Because this column vector can be written as a multiple of V1 plus the same multiple of V2. Is V1, V2 a basis for H? V1 doesn't have matching real numbers for the first 2 entries. Since V1 and V2 are not in H, which is defined as 2 matching entries followed by a 0, V1, V2 cannot be a basis for H. But let's note that those 2 vectors, V1 and V2, is a basis for the plane of all vectors of the form C1, C2, and 0. But H is only a line.